Equilibrium is the condition that occurs when there is no angular acceleration or linear acceleration. So the object is either at rest or is moving with a constant angular and or linear velocity. This implies that the sum of the forces on the object is zero. The net force is zero, and this is in any coordinate direction. Also, the sum of the torques acting on the object is zero, since there is no angular acceleration. So when we have a condition of equilibrium, if we have an object that is either at rest or moving with a constant angular or linear velocity, we know that we can sum the force components in any direction and set equal to zero, and we can sum the torques on the object and set those equal to zero to solve for any unknowns that might be in our problem. In order to compute the torque due to the gravitational force, we always pretend that all of the weight is concentrated at a single point at the center of mass, which is also called the center of gravity. So if you have an extended object, the gravitational force will exert a force on that object, and in order to find the moment arm to use with that gravitational force to calculate the torque, we pretend that all of the mass is located at the center of gravity, and that is where the force is applied. So for the gravitational force, the moment arm always goes from the origin to the center of mass. Now, if the object is symmetric, we can usually guess where the center of mass is. We saw before how we can do that. It's where the object balances. It's in the middle of a symmetric object. If, on the other hand, your object is made up of many individual point masses, then you can calculate the x and y coordinates of the center of mass by summing each individual mass times its x coordinate and then dividing by the total mass. Or we can find the y coordinate by taking each individual mass times its y coordinate and then dividing by the total mass. So this is something we saw previously, how to find the center of mass, and that becomes very useful when we have gravity exerting a torque on our object. So let's look at an example where we can apply these ideas, both finding the torque from gravity and also looking at an object that is in equilibrium. So in this example, we have a 500 Newton uniform rectangular sign, which is 4 meters wide and 3 meters high. It's suspended from a horizontal 6 meter long uniform 100 Newton rod. The left end of the rod is supported by a hinge, and the right end is supported by a thin cable, making a 30-degree angle with the vertical. So the problem asks us two questions. We need to find the tension in the cable, and then we also need to find the components of the force exerted by the hinge on the left end of the rod. So as before, we need to first draw a picture of this example situation and show all of the forces. So I'm going to draw a picture of the rod. The rod is the thing that could potentially be pivoting if all of the forces did not balance on it. So if I'm drawing a picture of the rod, here's my rod, and I know that at the left end of the rod, it is supported by a hinge. And I'm going to make the hinge my origin, and that's for multiple reasons. One is that the rod, if it was allowed to pivot, would pivot about this hinge, but also initially I don't know, I want to find the tension force of the cable, and I don't know anything about the forces exerted by the hinge yet. And so if I put the origin there, my moment arm for the hinge forces will be 0, and they won't appear when I sum the torques, which, as we'll see, will be convenient for this problem. So if I think about the other forces that are acting on my rod, there's going to be this tension force from the cable, and the tension force is exerted at a 60-degree angle. So we can see that there's a 30-degree angle at the top of the cable. The cable makes a triangle, and so since the top is 30 degrees, the other angle must be 60 degrees, since those two angles have to add up to 90 degrees. So we have this 60-degree tension force, and then we have other forces acting on our rod as well. Now, so two of those forces come from gravity. So there is the weight of the rod itself. And as we remember before, gravitational forces are weight or weights. When we want to find the torques that they create, we draw them as if they are emanating from the center of mass. So since this is a uniform rod, the center of mass is right in the middle, and the gravitational force, or the weight, of 100 newtons for this rod we'll draw it exerted from the center of mass. And we know that that center of mass, since the rod is 6 meters long, that the center of mass of the rod is 3 meters away from the hinge. Then we also have the weight of the sign pulling downward on the rod, and the sign is hanging on the right end, and we also know that the sign is 4 meters long, and it's 4 meters starting from here. So the middle of the sign is going to be 2 meters, half of that distance, from the left edge, or the right edge. So the sign starts here, it goes 4 meters, and so half of that would be 2 meters, and that's where the middle of the sign is. So we draw the weight from the sign, which is going to be 500 newtons. We draw that as emanating from the center of mass in the horizontal direction of the sign, and the sign's center of mass is 2 meters from this end of the rod. So we know that this distance here is 2 meters. All right, so there are most of the forces acting on the rod. There is one more force, and that's the force exerted by the hinge. And right now, we don't really know anything about that force. We don't know how big it is. We don't even know what direction it's going. So I'm just going to take a wild guess and say that this is the hinge force, F sub h, and I will figure out what the direction is and what the magnitude is later. All right, so the next thing we'll want to do is, in order to find our tension force here, is to sum the torques acting on the rod. And since the rod is stationary, it's in equilibrium, we know the sum of the torques is going to be equal to 0. So we should write down what are all of the torques acting on this rod. So first off, the weight of the rod is going to exert a torque, and we know that torque generally is RF sine theta. The distance of our moment arm from the hinge, the origin, to where we draw the weight being applied is 3 meters. So that is our moment arm, the length of our moment arm. The amount of force is 100 newtons. And then the sine of theta, well, theta is 90 degrees between the direction of the moment arm and the direction of the force, and the sine of 90 is equal to 1. So I would just be multiplying by 1. Then I also need to figure out, is this a positive torque or a negative torque? Would this cause motion in the clockwise or the counterclockwise direction? So if I think about grasping this rod at the origin, and I think about pulling with this force, if this is the only force acting on the object, and if I'm holding it here, that would cause the end of the rod to rotate downward. This would pull downward, and that would cause a clockwise rotation about the origin. So since it causes a clockwise rotation, this is a negative torque. So I need a minus sign there. So next, let's think about the weight of the sign. So the weight of the sign is being applied at what distance from the hinge? Well, I know that the entire rod is 6 meters long, and I know that the force being applied by the center of mass of the sign, that's the center of mass is 2 meters from this end. So from here to here is 6 meters, from here to here is 2 meters. So 2 meters subtracted from 6 meters would give me 4 meters. So there's 4 meters from here to where this force is applied. So my moment arm is 4 meters. The amount of force is 500 newtons. And this force is also going to cause a clockwise rotation. So if I imagine holding the rod here at this end and pulling with this force, it would cause the end of the rod to move downwards, which is in the clockwise direction about the origin. So that's also going to be a negative torque. So then let's worry about the tension force from the cable. The tension force is being exerted at this end, and the tension force is upward 60 degrees from the moment arm, and the tension force is applied at the far end of the rod from the hinge, so that would be 6 meters away. So that's going to be 6 meters for the length of my moment arm times the tension force, which I don't know yet, so I'll just write down T, times the sine of 60 degrees, because there's 60 degrees from the moment arm, which goes from the origin out to where this force is applied, and the direction of the force. Now, as far as the sine goes, if I imagine just pulling with this force and seeing how the rod would move, if I was just pulling with this force, it would tend to pull the end of the rod upward. So that represents a counterclockwise rotation of the rod. So this would be a positive torque. And all of these torques sum to 0. Oh wait, there's one more torque, or one more force on my rod, and that's this hinge force. So the hinge force is exerted at an unknown angle, and it has an unknown amount, but what is its moment arm? Well, the hinge force is applied at the hinge, and I've designated the hinge as my origin, so the distance from the hinge to where this force is applied is 0. So since the moment arm is 0, that's pretty much it. That force exerts no torque about the origin because it's at the origin. So I don't have to worry about that hinge force in the problem, which is why one of the reasons why I chose the origin to be there. All right, so I have all of my torques summed to 0, and now I can solve for my unknown, which is the amount of tension in the cable. So if I multiply these things out, the 3 times 100 newtons and then the 4 times the 500 newtons, if I multiply those together and then bring that to the other side of the equation, I get 2,300 newtons times meters. So that's just the 3 times 100 plus 4 times 500. And then that's going to be equal to 6 meters times T sine of 60 degrees. So then I can just divide both sides by 6 meters times sine of 60. The tension force is 2,300 newtons times meters divided by 6 meters times the sine of 60 degrees. So that's going to give me a tension force of 443 newtons. Okay, so now I know the tension force. That's the solution to part A. So then for part B, I actually do want to find the horizontal and vertical components of my hinge force. I want to find what's the X component of the hinge force and the Y component of the hinge force. So in order to do that, I think it's most convenient to sum the forces in both the X and the Y direction. I know that the sum of the forces in both directions is going to be 0 since the rod is not moving. So if I sum the forces in the X direction, that's going to be 0. And the sum of the forces in the X direction is, well, I'm going to have some X component to my hinge force, likely. So I'll say hinge force X component. This is all in the y direction. This weight is all in the y direction. So then I do have the tension force. And let me just draw it separately to make it a bit easier to split into components. So here is my tension force. This angle is 60 degrees. And this would be the x component and then the y component. So we look, the x component is adjacent to the 60-degree angle. So if I look at the cosine of 60 degrees, that's going to be the x component over the hypotenuse, which is the tension force. And so the x component is going to be t cosine of 60 degrees. And I notice that this tension force is pulling in the negative x direction, as I've defined it. So this would be minus t cosine of 60 degrees. And those are all of the forces that could potentially act in the x direction. So those sum to 0. So in order to find the x component of the hinge force, I just need to take this to the other side of the equation. I know what t is. So the x component of the hinge force then is going to be t cosine 60 degrees, and t is 443 newtons times the cosine of 60 degrees. So the x component of the hinge force then would be 222 newtons. So there's my x component. And then similarly to find the y component, I'll want to sum all of the y component forces, and those will sum to 0 since nothing is moving. And so that's going to be equal to the y component of the hinge force, so force hinge y, so this y component of the hinge force. And then I have the 100 Newton force pulling in the minus y direction. I have the 500 Newton force also in the minus y direction. And then I have this component of the tension in the positive y direction. And this component is opposite the 60-degree angle, so that's going to be plus t sine of 60 degrees. So it looks like, once again, I can take all this stuff to the other side of the equation in order to find the hinge force in the y direction. So the hinge force component in the y direction is going to be 100 newtons plus 500 newtons, and then minus t, which is 443 newtons, times the sine of 60 degrees. And if I plug that into a calculator, I will get a y component of the hinge force of 216 newtons. All right, so that gives me the x component and the y component of the hinge force, which is what the problem was asking for. All right, so let's look at another example. In this example, we have a ruler. The ruler is hanging by a string, and the string is attached at the 40 centimeter mark. We also have a couple of weights. We have a 500 gram weight, which is hanging at the 25 centimeter mark, and we have a 200 gram weight that we want to place on the ruler. And the question is asking, where do we put this second mass in order to achieve equilibrium? We want the ruler to balance on its string that it's hanging from. So let's take a look at this problem. First, we'll want to draw a picture of the ruler and show all of the forces on it. So here is our ruler. And we know that we are hanging the ruler at the 40 centimeter mark. So we have some tension force from a string being applied at the 40 centimeter mark. We also know that we have this 500 gram weight hanging at the 25 centimeter mark. So this is going to cause a force. This weight will cause a force here, and the amount of force is going to be equal to 0.5 kilograms. So I've just taken the 500 grams and converted to kilograms, times G, times 9.8. That's going to be the weight here. And then what about the moment arm? Well, the suspension is here, and this weight is here. So I do have to pick an origin, and I will pick the place where the string is hanging, or where the ruler is hanging from the string, as being the origin, because that's where the ruler would be pivoting around, and I also don't know what the tension force is yet, so it's convenient that that have a 0 moment arm. So I'm going to put my origin here, and so I will need to know what is the moment arm, the distance from the origin to where this force is applied. And since this is the origin, and the origin's at 40, and this weight is at 25, 40 minus 25 is 15. So this moment arm is 15 centimeters. So there's 15 centimeters. This weight is 15 centimeters away from the origin. All right, so then I also am going to be hanging this 200 gram mass somewhere over here. I don't know where yet, so I'll just draw it here. The moment arm is unknown. In fact, that's what I want to find. What is the moment arm? And but I do know the weight that I'm hanging, so that's going to be 0.2 kilograms times G times 9.8. That's the weight of this mass, wherever it's hanging. And then there is one more force I have to worry about, and that is the mass of the ruler itself. And that force, that weight of the ruler, I'm going to show acting at the ruler's center of mass. So the center of mass of the ruler is at the 50 centimeter mark. So this would be the weight of the ruler exerting the torque about the origin, and this is going to be equal to the mass of the ruler times G. And the moment arm for the weight of the ruler, this distance, well, this is the 50 centimeter mark, this is the 10 centimeter mark where the string is, and so that's going to be 10 centimeters for that moment arm. All right, so now I have enough information to write down the sum of the torques that are acting on this ruler. And I know the sum of the torques is going to be 0 because I want the ruler to be balanced and I want it to not be rotating, not accelerating. So if the sum of the torques is equal to 0, I need to figure out what are the torques from all of these different forces that are acting on the ruler. So let's start with this force here. So the moment arm for that force is 15 centimeters or 0.15 meters. And then the amount of force is 0.5 kilograms times 9.8. That's the weight, meters per second squared. And then is this a positive torque or a negative torque? Well, if I imagine holding the ruler or having the ruler suspended from the string at the origin and pulled down with this force, this end of the ruler would move downward, this end of the ruler would move upward, and that represents a counterclockwise rotation of the ruler. So if I have this one going up, this end going down, the ruler is tipping in the counterclockwise direction, and so that's a positive torque. So I can leave that with just, leave that torque as just being positive. So next, let's think about the string. So we know that the string has an amount of force equal to T. What about the moment arm? Well, the string is applied at the origin. The distance from the string force to the origin is 0 since it's right there. And so the moment arm is 0, and the string force does not appear or doesn't contribute to the sum of the torques about the origin. All right, so next let's think about the weight of the ruler. So we have the mass of the ruler times 9.8 meters per second squared. And is this going to be a positive torque or a negative torque? Well, if we imagine holding the ruler here and pulling down with just this force, this end of the ruler would swing this way, this end would swing upward, and so that represents a clockwise motion of the ruler, and so this is going to be a negative torque. So that one would be negative. And you'll notice too that I'm not putting in the sign of an angle, because the sign of the angles, these are all right angle moment arm to force vectors, and so the sine of 90 degrees for all of these is going to be equal to 1. So the last force I have to look at is this one here, and so that's going to be equal to, let's see, that torque, well, I don't know what the moment arm is. I'm calling that R. So I have R for the moment arm. The amount of force is 0.2 kilograms, and then times G, which is 9.8 meters per second squared. And then this force, it's in the same direction as this one on the same side of the origin. So as you might guess, this is also going to be causing a clockwise rotation if this was the only force applied. And so this is going to also be a negative torque. And all of these torques sum to 0. All right, so the thing I want to find is I want to find this moment arm. I want to know where I am hanging this mass. And so I need to rearrange this equation so that I have this on one side and everything else on the other side. And so let's see. So if I move this term to the other side of the equation, I would get R times 0.2 kilograms times 9.8 meters per second squared. That is equivalent to 1.96, and the units would be newtons, and that's going to be equal to 0.15, so all of this multiplied together minus the mass of the ruler times 9.8. So all of these things multiplied together is equivalent to 0.735 newtons times meters. And then I need to subtract from that the mass of the ruler times the mass of the ruler times I forgot here to multiply this by the moment arm. Oops. So mass of the ruler times G, and then I have to multiply that by the length of the moment arm. So that's the force, but I also need the moment arm, which was 0.1 meters, 10 centimeters. And so that's going to give me, for this term, 9.8 times 0.1 is 0.98, and then the units would be meters squared over seconds squared. All right, so then I can divide both sides by 1.96, and I also need to stick in what the mass of the ruler is. So R is going to be 0.735 Newton meters minus the mass of the ruler, which is 0.1491 kilograms, times 0.98 meters squared seconds squared, all divided by 1.96 newtons. So that gives me an R, a moment arm, which is equal to 0.3004 meters, or 30.04 centimeters. So that means that the ruler, okay, so where this needs to be hung 30.04 centimeters away from where the string is attached. So what mark is that on the ruler? So if this is the 40 centimeter mark, and I need to add to the 40 centimeter mark 30.04 centimeters, that means I should hang that mass at the 70.04 centimeter mark. So if I look at the markings on the ruler, I hang this weight at 70.04 centimeters, and then the ruler should balance. So here's another question. Can an object be in equilibrium when only one force acts on it?